In this lecture, we will cover lasso regression. Lasso regression is a type of machine learning, and specifically it's a type of supervised statistical learning. So in this lecture, I'll first provide you with an overview of lasso regression, and then we'll talk about the assumptions of lasso regression. Then we'll talk about statistical significance and practical significance in the context of lasso regression. So let's start with that overview. So what does LASSO stand for? Well, LASSO stands for Least Absolute Shrinkage and Selection Operator, or LASSO. Now here I've written it in all caps, but I've also seen it written as LASSO all lowercase as well. So you might see it spelled or both ways in terms of case sensitivity. So lasso regression, as I mentioned previously, is a form of supervised statistical learning, meaning it's a type of machine learning, and it's aimed at improving prediction. So if you're going to use lasso regression, often your overarching goal is to develop a model that's going to be as predictive as possible of a particular outcome you're interested in predicting. So we're really talking about predictive accuracy or classification accuracy, depending on what type of model you implement with lasso regression. So lasso regression effectively selects only the most important predictor variables for predicting a particular outcome by shrinking the regression coefficients associated with the least important predictor variables to zero. Now, it's not going to typically shrink every regression coefficient to zero. However, it does typically shrink a number of them to zero, and one of the purposes of doing so is to create a more simplified model. And in other words, this creates a more parsimonious model too. And this really comes based on this tug of war between model accuracy in terms of prediction, as well as model parsimony in terms of the number of predictors. So this is a really, really good type of model if you have a large number of predictor variables that you would like to determine which are going to be the ones that are most important for predicting a particular outcome variable. And above and beyond that, selecting those that are going to be best at maintaining and achieving predictive accuracy or classification accuracy, again, depending on what type of model you implement with lasso regression. So in general, the following are reasons for applying or using or implementing lasso regression. The first is to avoid overfitting a model to the data on which it was originally trained or estimated. Now, this can be problematic when you overfit, and this can happen with conventional regression techniques such as ordinary least squares, linear regression, as well as generalized linear models such as logistic regression. Now, this is going to become even more problematic when it comes to overfitting when there's a large number of predictor variables. And so lasso regression can step in and it can make sure that you're not fitting a particular model to be too specific. In other words, almost too predictive. It reduces too much error in the prediction for the data on which it's trained, which means that then when you try to generalize that model and apply it to other data from the same sample or from the same population rather, it's not necessarily going to perform very well. So lasso regression uses that penalty I mentioned before in which it shrinks the regression coefficients associated with the least important predictor variables to zero or towards zero. This is going to be a way in which it can help avoid overfitting a model to the data. Now, one of the second reasons for applying lasso regression is that, as I mentioned before, it can be used to select the most important predictor variables, which in this context are often referred to as features. And so sometimes this is called feature selection as part of lasso regression. And so again, if you have a large number of predictor variables, let's say 20 or 30 or more predictor variables, sometimes this could be used in different settings where you might have hundreds of predictor variables. This can be a really useful technique in terms of calling down that number of predictor variables and identifying only those that are most important for predicting the particular outcome. And so, as I mentioned before, some of those predictor variables will even be zeroed out, which essentially means they're eliminated from actually predicting the outcome of interest. So a big part of lasso regression is that it is what's called a regularization method. And specifically, it's an L1 regularization method. And it's related to other types of regularization methods such as ridge regression and elastic net. So lasso regression, ridge regression, and elastic net have a lot of similarities in common. And so once you get comfortable with one, it's pretty easy to learn how to do the others. And sometimes what we'll do is we'll actually use 2 or 3 of these regularization methods in order to predict a particular outcome, and we'll see which performs better. in terms of its predictive accuracy. Now, the purpose of regularization is to reduce the variance of parameter estimates, which, for example, are the regression coefficients. And even if this reduction in the variance of parameter estimates comes at the expense of introducing some additional bias. And ultimately, this is going to mean finding the optimal level of model complexity. Now, in terms of variance, what we're talking about there is variance of the regression coefficients themselves, so variability in their estimates. And then when we're talking about bias, we're talking about the extent to which those parameter estimates, those regression coefficients, deviate from the true parameter values, the true population level values that we're attempting to estimate, okay? And so what's interesting is that with lasso regression, we are going to see that reduction in variance at the expense of some additional bias, whereas with ordinary least squares, traditional linear regression, we typically see the opposite, which is OLS, or ordinary least squares regression, is going to be in favor of reducing bias at the expense of introducing more variance around those parameter estimates. So another part of lasso regression, this has very much to do with regularization, are the tuning parameters. And specifically, there's one tuning parameter that is really about regularization when it comes to lasso regression, and that is the lambda tuning parameter. But there's also another tuning parameter that's called alpha. Now, we're not going to focus so much on alpha, and this is referred to as a mixing percentage tuning parameter. And the reason we're not going to focus on it is that when you're running lasso regression, you set alpha to 1. In other words, alpha is equal to 1. It becomes a constant. If you're running ridge regression, you'd set alpha equal to 0. And so because we're keeping it as a constant, we're not going to focus on it in this lecture. Instead, we're going to focus on lambda because this is actually a parameter that we're going to vary and to see at what level it really optimizes the prediction. Okay, so we're going to focus on training, or we're going to focus on lambda because it's actually going to be varied during the model training process. Now, the lambda tuning parameter, lambda is represented by this, the Greek letter lambda here, or the spelled out word here as well. You might see it displayed differently depending on where you're reading. Now, the lambda tuning parameter is going to place a constraint on the maximum absolute value of the regression coefficients in the model, and it's going to add a penalty, which I was mentioning earlier, to any non-zero regression coefficient. So it's going to pull them towards 0, and some of which, as I mentioned before, it's actually going to zero out, meaning those regression coefficients or parameter estimates are going to become 0, which means they're essentially or effectively removed from the model in terms of prediction. And so again, this is how lasso regression institutes a form of feature selection or variable selection. So continuing on with the idea of the lambda tuning parameter, there are different effects of different lambda values when it comes to our lasso regression estimations. Now, when lambda is 0, the results of our regression model will actually approximate a conventional regression model. So for example, if we're doing linear regression using a lasso regression framework, then if we set the lambda to 0, then our results will tend to approximate a conventional ordinary least squares linear regression model. And conversely, if we were doing this with a generalized linear model such that we were trying to predict a binary or dichotomous outcome variable, so specifically we would be using a logit model or logistic regression model, when lambda is set to 0 in a lasso regression, the results will approximate just a standard logistic regression model, for example. Okay. Now, when lambda is set to 0, no of the regression coefficients associated with the predictor variables are going to shrink to 0 or be eliminated. So again, this is why it will reflect a conventional regression model or a traditional regression model, however you'd like to call it. Now, when that value is large, the regression coefficients with smaller absolute values will tend to shrink towards 0. So they're going to be pulled towards 0. And if lambda, or when lambda becomes too large, all those regression coefficients or parameter estimates are going to shrink towards 0. So essentially, you'd make the model so parsimonious in terms of the number of predictor variables that you would eliminate all the predictor variables. And so obviously that's not likely going to aid prediction of the outcome variable if you zero out all the regression coefficients. Now, another thing to consider too, is I was talking before about these ideas of model variance and bias. As lambda gets smaller in terms of its size, the variance will tend to grow larger. Okay, and so this makes sense because remember, as lambda gets smaller, meaning it's moving closer to zero, it's going to start approximating a more traditional form of regression, such as for linear regression, an ordinary least squares model. Now, as lambda gets larger, the bias is going to grow larger as well. So this means that the tendency for our parameter estimates or regression coefficient estimates to deviate from the true population values is going to tend to get larger. Okay, so you have this kind of tug and pull here again, where you're trying to find this sweet spot in terms of tuning this lambda parameter to be its optimal level or its optimal value. So in terms of the optimal lambda, in general, the optimal lambda will strike a balance between model accuracy and model parsimony. So in terms of accuracy, here's an example of a common data visualization that you'll see when it comes to looking at the effects of different lambda values on model accuracy metrics such as the mean squared error or the root mean squared error, or sometimes you'll see something similar with the R squared value as well. And what you can see here in this plot, and note that on the x-axis we've actually taken the logarithm of lambda, and this just aids our interpretation here visually as we're trying to look at this plot. Here we have log lambda in relation to mean squared error. And so what we want is we want as low of mean squared error as possible. And typically this is how we select the optimal lambda value, is finding that value at which lambda is lowest, or lambda results in the lowest amount of model level error. And so you can see here that as lambda right around, it kind of looks like this log of lambda around -4 or so, maybe a little bit less than that in this particular plot, you'll see that that seems to be the sweet spot here in terms of reducing mean squared error. Okay, so often we're looking for that minimal level of, if we're using mean squared error as the metric, or if we're using root mean squared error, we're looking for that minimal level of mean squared error. Sometimes you'll do one standard error around it and try to and find in terms of finding the ideal log lambda value, and specifically, ultimately, we're interested in just the lambda. So again, you can see the effects of different lambda values, and as you'll note here, the error tends to get really, really high when the long lambda value grows larger and larger and larger. Okay, so this would correspond to a larger lambda value, and you can see the error really kind of skyrockets and plateaus here, and this is likely the point at which you have eliminated or zeroed out all the regression coefficients, and so you're not going to be able to improve any of the model-based predictions anymore. Essentially, you would be probably just as well off just taking the historical average of your outcome variable and using that into the future in terms of predicting the model if you eliminate all the predictors and their regression coefficients from that model. Okay. All right, so again, we're balancing model accuracy and model parsimony. Okay, so again, if you remember that lasso regression is often used when we have a large number of predictor variables in our model. So we also want to consider parsimony. We don't want too many predictor variables, as again, this can lead to overfitting our model to the data that we train the model on. And so here you can see a different plot. And again, we have on the x-axis the log of lambda here. Okay. And then you'll see, and this is just, I created this to be relatively simple. There's only 10 variables here displayed, but again, we typically use lasso regression with more predictor variables than 10, although we can use it with just 10 as well. And what you'll see here on the y-axis is the regression coefficient values. So you can see coefficient of 0, and then we have positive values and negative values here. And so as you can see, as lambda increases in size, you'll notice that some of the regression coefficients are going to start moving towards 0. So this is that regularization penalty that's taking place as lambda is tuned here, okay? And so as the log lambda increases, eventually you get to this point where you are going to have all the regression coefficients zeroed out, which you can imagine this invisible horizontal line here, and you can see how they all kind of converge here. This means that all these different predictor variables and their regression coefficients are 0, meaning that they're not used for prediction in the model anymore. So if we go back to the last plot, this would be this spot right here. Okay, and just again, remember that we're using log lambda here, so these values should not be interpreted in terms of just lambda before the logarithmic transformation. Okay. All right, so the next thing that we'll talk about is the model type selection. So lasso regression was originally developed to be used with linear models, meaning that we would use it with a continuous outcome variable was the way in which it was originally created. However, it's had a number of extensions in recent years, meaning that it can be applied to other families of models, such as generalized linear models as well. And so generalized linear models, this is the home of logistic regression. And so you can also do logit models, meaning that you can, lasso regression can handle a dichotomous or binary variable as well. And so that's something to consider too. You're not limited to just outcome variables that are continuous in nature. You can also look at outcome variables that are non-normal or categorical in nature as well. Now, when we use lasso regression, it's really advisable to do some kind of cross-validation process when training the lasso regression model, as this can actually improve your model's predictive performance, as well as how well the model is going to ultimately generalize to other data from the same population, and ultimately, because of that generalization, be more likely to predict the outcome with greater accuracy. In other words, achieve higher predictive accuracy, which is really what we want here with lasso regression. Again, the emphasis is really on prediction here, okay? And so there's different ways in which we can cross-validate the data, but k-fold cross-validation has really emerged as kind of a gold standard approach. And so this is one that I'd advise you to use, assuming you have a large enough sample to work with to begin with. Because with k-fold cross-validation, you will be behind the scenes splitting the data, and often we'll split the data initially in terms of having, let's say, 80% of the data randomly assigned to a training data set, and the remaining 20% randomly assigned to a test data set. And then within that 80% of the data that went to the training data set, as part of k-fold cross-validation, we actually are going to split or partition the data further into separate equal size samples or subsamples, and then we're going to actually train the model on the different combinations of the data from these subsamples and validate along the way. And so this, again, k-fold cross-validation does offer a nice framework for cross-validation, and especially when the lasso regression model is trained using k-fold cross-validation on a random subsample of the original data and then evaluated using that separate holdout or test data frame or subsample from the original data that I mentioned previously. So again, this is going to be a luxury of having sufficiently large amounts of data if you'd like to do k-fold cross-validation, but k-fold cross-validation can really go a long way in making sure you really do arrive at that optimal lambda value. And typically when you do this across a number of samples and then find the average or the optimal lambda across each one of those different folds in, let's say, a k-fold cross-validation, you can then, that average lambda value that was optimal across all those folds can then serve as the final version of that tuning parameter that then you can apply to all of the data. And typically this is going to yield a more predictive model in terms of its accuracy. So in other words, when we're doing k-fold cross-validation in the way I just described, it's really a process that's going to blend model training and cross-validation with predictive modeling, or in other words, predictive analytics framework, okay? And so predictive analytics is really at its core that idea of you train the model on one set of data, and then you are going to test that model on a separate set of data that's fresh, that's that holdout data that has not yet been seen by the model in terms of where it was originally trained. So let's talk about assumptions in terms of statistical assumptions that should be met in the case of lasso regression specifically. Well, these assumptions will really depend on the type of model that you use for estimation. So remember, I talked about a little bit ago that idea of model type selection. I said you could have a continuous outcome variable and do more traditional linear modeling, or you could use an implementation with generalized linear models where you could have a categorical variable, for example, or even more specifically, a binary or dichotomous variable. So you really want to consider what are the statistical assumptions that need to be met for whatever specific type of model you select to implement using lasso regression. Now, one point I will make about lasso regression more generally is that by nature, lasso regression can help you address multicollinearity, which can pose problems for traditional forms of regression, such as ordinary least squares, linear regression, or generalized linear models, logit models, logistic regression, and so forth. And so that is an advantage of lasso regression. And part of this, the reason that it can help address multicollinearity has to do with that regularization, that penalty that it implements in terms of as Lambda increases, pulling those parameter estimates or those regression coefficients closer to zero or entirely to zero for some predictor variables. Let's move on now to talk about statistical significance and then finish up with practical significance. So like many other statistical learning or supervised, more specifically supervised statistical learning techniques, which broadly fall under the umbrella of machine learning methods, the overarching goal of lasso regression is model prediction. And so thus the statistical significance of the regression coefficients or the parameter estimates is not often of interest or even computed at all. You can definitely generate the regression coefficients fairly easily once you find that optimal lambda value. However, again, the statistical significance of each one of those regression coefficients is typically not of interest. And there's a few reasons for this. One is that often this is done with very large sized amounts of data where traditional statistical significance testing may be less relevant, meaning that we would often meet many of the conventional thresholds for statistical significance for a lot of our variables, and when we have very, very large amounts of data. But another reason is that this type of modeling process using lasso regression is really about prediction, as I've mentioned a few times already. It's not so much about understanding the variables that you have as predictors in the model and why they're predictors. So it's not necessarily it's not going to be theoretically driven. It's more about how do we optimize the predictive accuracy of the final model that we achieve by tuning that lambda parameter. So what we're really interested in when we're focusing on lasso regression are indices or metrics that have to do with model fit and prediction. And so these are going to be typically our main focus. And so examples of these include your root mean squared error, or RMSE, your R squared variable, so your variance explained. It's another model fit indicator, as well as if you're interested in classification and you have categorical outcomes, classification accuracy, kappa statistic, and so forth might be also other metrics we're really interested in here. And so these really have more to do with practical significance, which I'll talk about next. But before moving on, I do want to point out that in terms of the statistical significance of specific regression coefficients or parameter estimates when it comes to lasso regression, there has been some preliminary work on developing significance tests for lasso regression coefficients. And if you want to learn more about that, Lockhart, Taylor, Tibshirani from 2014, they have an article in a statistics journal in which they introduce a method for calculating performing more traditional statistical significance testing on the regression coefficients derived from a lasso regression model. Now, just backing up though, I do want to emphasize what our goal here is with lasso regression. So if you think more broadly about the goals of science, typically we'd say the goals of science and research in general are to describe, explain, determine the cause of, and to predict. Now, with lasso regression, we really just zero in on the prediction part of it. We're focusing on predicting with not much thought towards explanation in terms of understanding a phenomenon of interest or a process or describing it or even determining the cause of it. We're basically saying what are the features or the predictive variables we can put in this model, and we have a lot of them presumably if we're doing lasso regression, that can then best predict that outcome variable in terms of doing it accurately again and again in the future when we get more data from that same underlying population from which the original training data came from when we trained our lasso regression model. So let's jump on now to practical significance and round out this lecture discussing what we mean by practical significance. Now, again, this is really going to be at the model level that we're interested in practical significance when it comes to lasso regression. And we can interpret the magnitude of a model's fit, or how well the model fits the data, as well as its predictive and performance or prediction performance, prediction accuracy, whatever you're focusing on. And we can do so using metrics or indices, as I mentioned before, that are specific to the type of model that's implemented using lasso regression, such as if we're using linear regression, typically the metric that we're interested in terms of tuning that lambda parameter is going to be to try to minimize the root mean squared residual, or root mean squared error, the RMSE, or the R squared value. Sometimes the mean absolute error is also used. Now, if we're interested in, let's say, classification, then typically we will be interested in improving the classification accuracy or the kappa value as another indicator of how well our model is classifying cases into specific levels of the categorical outcome variable. Okay? But that's really what we mean by practical significance here, is the predictive performance. So what is the magnitude of the predictive performance and accuracy of the lasso regression that we have trained and that we are ultimately going to apply to new, fresh, holdout data that haven't yet seen the model. So just to wrap things up a bit, and here are the, as I mentioned before, here's the typical metrics that we use for linear regression models, the RMSE and R squared, as well as for, as I mentioned before, when we're talking about logistic regression and generalized linear models more broadly, classification, accuracy, and which you'd find in the confusion matrix, as well as kappa, which you typically also get generated in the confusion matrix, are typical metrics that we would use in those contexts. So it really depends, again, on the specific type of model that you select in, with which to implement lasso regression. So to do a brief recap, we started off by doing a conceptual overview of what lasso regression is and what it means, and what regularization means, what a tuning parameter is, what lambda is, what alpha is. And those are two specific types of tuning parameters. Remember, one, alpha is the mixing percentage, and we just set that to 1. And then lambda is that tuning parameter that, as the name implies, we're actually going to tune here and try to find the optimal value or the optimal level. And then we also talked about the value of implementing lasso regression using a k-fold cross-validation process within a broader predictive modeling or predictive analytics framework. We then moved on and talked about statistical assumptions, and finished off by talking about concepts related to statistical significance and practical significance when it comes to lasso regression. So that wraps up the lecture on lasso regression.